So we'll continue discussion of different types of hybrids available in the marketplace. The next one showing here is a Saturn wheel green line hybrid system. GM come out a couple years ago. In this diagram, you can see that this hybrid is many people refer to as a micro hybrid. It has a small electrical motor connected to the engine cranking shaft through a tension belt. So that tension assembly would give you some assistance during start of the vehicle. There's a nickel metal hydride battery pack at the back, behind the back seat of the vehicle, which is also a very small battery pack. The motor itself is a Clopole type PM, but it's a PM, it's a Clopole type motor, which is rated only at 4 kilowatts. So therefore, for this type of vehicle, it's not likely to become a plug-in hybrid because that motor is merely used to assist starting the vehicle. So that's the one. Also, because of smaller size of motor in the engine, you get some advantage. For example, very low cost increase, maybe about a couple $100 increase in the vehicle cost, but then you also get smaller percentage of fuel economy, maybe 5% over all the vehicle system. So the next few slides, we're going to move on to discuss a few more complex hybrid systems. Now, some of the systems has been produced by OEM, but some of the system may not have been, but it's just a type of configuration that can be used as a potential hybrid vehicle system. So one of the systems we're going to discuss, very first one is the dual clutch HEV. So let's go back to the slide. On this drawing, we have a dual clutch system, and that consisted of a dual clutch system, 2 electrical motors, and an engine. So let me start by looking at the diagram from the very bottom right corner. At the very bottom right corner, you'll see the fuel tank. So what you can see is the fuel tank supplying fuel to the engine, which has 4 round cylinders showing there. So the engine takes the fuel, and it's connected, the output of the engine shaft is connected to a dual position clutch. You can see that the clutch has 2 different colors. One color is yellow, the other color is purple. So we're going to refer those 2 colors for further discussions. Depends on the control, the clutch, the 2 clutches, which one connect to the yellow engine, yellow gear, one connect to the purple gear. The 2 of them can be connected to the engine. So it depends on the control. Either one can be connected to the engine, but only one at any given time. So let's assume that the yellow gear is connected. The yellow gear is engaged with the engine. So now the gear will move with the engine. Now it depends on how soon the clutch would engage. So the yellow gear speed will gradually start from 0. If at the beginning engaging, the yellow gear will start from 0 speed all the way to the same as the engine speed after the whole engagement. If you look carefully, the yellow gear, the bottom, the yellow gear that connects to the clutch, the bottom one has a gear connected to the gear that has a solid shaft. And that solid shaft extended through the hollow shaft. So we're going to talk about hollow shaft in the next moment. But if you look at the solid shaft, it extended all the way to the right, to the left, across the purple gears, and is connected to the 3 yellow gear pairs, 1, 3, and 5. So those 3 yellow gears are connected to the purple, the solid shaft, the yellow gear. And you can see that 1, 3, and 5, they are all connected to the driving shaft, and that driving shaft is connected to the final drive and the wheels. So between 1 and 3, 3 and 5, you can see there is little component that is called a synchronizer. So the 3 gears, which one will rotate would depend on which synchronizer is synchronized. So if the synchronizer synchronized gear number 1, gear number 1 will rotate with the solid shaft. If 3 is engaged, then 3 will rotate with the shaft, solid shaft, which means 3 is going to drive the wheels. If 5 is engaged, the synchronizer of 5 is engaged, the gear 5 is going to rotate with the solid shaft, which drives the vehicle. So depending on which synchronizer is engaged, the gears are selectively used to drive the vehicle. At low vehicle speed, apparently you want to use gear number 1. At higher vehicle speed, it may be 3 or 5. It depends on the vehicle operating condition. So let's assume at the beginning of the driving, gear number 1 is engaged. So now let's look at the gear number 1 is engaged. So torque is now transmitted from engine to clutch to yellow gear and through solid shaft to gear number 1. Then gear number 1 drives the final drive. So that's how torque is transmitted from engine to the final drive. When the vehicle speeds up, the gear number 1 is not able to do transmission anymore. So what you're going to do is, before you change clutches, you're going to synchronize gear number 2. So if you look at, that's the purple gear. So the purple gear number 2 is going to be engaged. When gear 2 is engaged, gear 2 is connected to the hollow shaft. So the hollow shaft is not driven by anything yet, but gear 2 is going to rotate with the final drive. So at that moment, what you're going to do is you're going to shift the clutch, the dual position clutch, from yellow gear to the purple gear. So now the torque from the engine is shifting from yellow gear to purple gear, which means it is shifting from gear 1 to gear 2. Because gear 2 is already engaged, so the torque transfer from gear 1 to gear 2 can be very smooth. So that's why this dual clutch transmission is very smooth. So the next moment, if vehicle speed keep increasing, you're going to engage number 3. And therefore, gear number 3 is going to rotate with the final drive. At some speed, you're going to shift clutch from purple to yellow again. So now gear 3 is transferring the torque. So you do the same thing for 4, 5, and 6. So this is a 6-speed, like a 6-speed manual transmission, but the gear transfer is done by automatic control devices, not by manual by the driver. So this is called a dual clutch. It's like automatic transmission, but it's like a manual transmission in performance. So in this system, because you have 1, 3, and 5 as a one set of gear, 2, 4, 6 is another set of gear. Each set of gear is connected to the clutch, which is connected to the engine. So now we add 2 electrical motors, one added to the yellow gear pair on top. If you look at above the clutch, there is a yellow gear connected to the output of the engine shaft. There is another purple gear also connected to the output of the engine shaft, but again, it's to the clutch, it's not to the engine, directly to the engine shaft. So those 2 electrical machines are connected. Yellow connected through the solid shaft to the yellow gear. Purple is connected from hollow shaft to the purple gear. So now if you are driving on the yellow gear, you can operate the yellow motor. So the yellow motor will provide additional assistance to the vehicle driving. So if we are operating on the purple gear, you can engage purple gear. You can drive the purple motor. So the purple motor will provide additional driving torque to the vehicle system. So this is perfectly a parallel operation. Anytime the vehicle is driven by a set of gears, you turn on that corresponding electrical motor. However, since you have 2 electrical machines and 2 sets of gears, it is possible to use this system as a series hybrid. The operating will be one of the motor is running as a generator, but the other one is running as a motor. So what we're going to do is, let's switch back to the diagram. In a series operation, we're going to engage, as an example, we're going to engage the purple gear with the engine. So engine is driving the purple gear. So the purple gear is driving the purple motor. So the purple motor becomes the generator to generate electricity. Then that electricity is delivered to the yellow motor. So the yellow motor is driving the yellow gear, and then the yellow gear is driving 1, 3, or 5, any one of the 3 gears. And that one of the 3 gears is synchronized to the final drive. So torque is transmitted from one or 3 or 5 to the final drive. Now, we don't synchronize 2, 4, and 5 because we are going to use 1, 3, and 5 to drive the vehicle. So in this case, the energy flow is from engine to purple gear to purple motor to yellow motor, then to yellow gear to the final drive to 1, 3, or 5. So that's in the series power flow. The engine is not directly driving the vehicle, but the electrical motor. So you can see that this system is very flexible. You can use either as a parallel or as a series operating. Now, there are some other parts in the system. If you look carefully, the voltage pack is about 300 volts. Apparently, depends on the vehicle design, can be higher or lower. The pump, fans, sensors, actuators, controllers, they're all part of the vehicle system. And then on the top right corner, you can see there's low temperature radiator, there's high temperature radiator with a fan. So that's, again, very similar to any other hybrid vehicle design. And then at the very top right corner, you can see the throttle control by wire, which means in all of the hybrid systems, the 2 pedals that you have, the braking pedal and acceleration pedal, they are not mechanically linked to the actual device itself. For example, the braking pedal. When you're pressing on the braking pedal, you're pressing on a sensor. You're not pressing on the hydraulic braking or the regenerative braking. You're actually generating a braking demand, and that demand is censored and sent to a controller. And then the controller will calculate how much braking power demand is requested, and then distribute between regenerative braking and hydraulic braking. Similarly, when you press on the acceleration pedal, you are not directly controlling the throttle of the engine. You are actually pressing on a sensor. And the sensor will send out information to the controller. And the controller will decide how much power is requested to drive the vehicle. And based on that vehicle condition and the component condition and your request, it's going to distribute the power between the electrical motor and the engine. It could be just the motor running, or just the engine running, or both running, or one as a engine running and then motor as a generator. So it really the drive-by-wire control system in hybrid electrical vehicle system. So this is a dual clutch system that was developed a few years ago, and apparently it's not been built into any actual commercial available vehicle yet, but due to the advantage of such a system, it's eliminating the traditional transmission, CVT, automatic transmission, and so on. So this system could become very popular in the next couple of years because of advantages that we explained. And the system is also a lot cheaper than a traditional CVT installed in a hybrid vehicle system. So that's something it should happen. And I have heard that there are countries in Asia that are working towards developing marketable model based on dual clutch systems. But in the North American market, apparently because of maturing the infrastructure to manufacture automatic transmission in CVTs, so dual clutch may not become popular because of the existing infrastructure that we already have. The next drivetrain we're going to discuss is the GM two-motor hybrid. And this is a patent filed by GM many years ago, and it's also the topology that is used in many of the GM, Chrysler, and BMW hybrid system. A number of years ago, the 3 companies built a joint venture collaboration to develop powertrain systems to be used by each of the participants. So right now, there are a number of two-motor hybrids available from GM Chrysler. And this is the basic, this diagram shows the basic topology of that system. Now again, we're going to start to look at from left to right. So from the very left, there's an engine, and between engine and the planetary gear, there is a clutch 16. So clutch 16 is used to engage and disengage the engine. Just in case the engine is off, the engine can be disconnected from the vehicle system to save additional energy. The clutch output is connected to the ring gear of the planetary gear. So if you look at the planetary gear, there are two planetary gears. Okay, there's one to the left, there's one to the right. The planetary gear we're looking at right now is the one to the left, which is composed by 52, 56, and 40. Okay, so you can see that the gear, if you look at 40 or 50, the 50 is connected, that's the ring gear, that's connected to the engine output or the clutch output, which is the same thing. The carrier, 56, is connected to a solid shaft. And if you look down to the right, the solid shaft all the way connected to 18, where 18 is connected to the final drive, which means the carrier is connected to the final drive. And then let's come back to the planetary gear again. If you look at the center of the planetary gear, 52 is the sun gear. So the sun gear is connected. The sun gear is connected to electrical motor 1. And electrical motor 1 is 26. So 26, you can see that's the electrical motor. The top two wires are connected to the ECU, which means you're going to take power to control the electrical motor. But the inside, the rotor is connected to 52, which is sun gear. So right now, if we don't look at the rest of the vehicle yet, you can say that engine is connected to ring gear, motor is connected to sun gear, carrier is connected to the output. Therefore, this is a speed coupling system. A speed coupling system. It combines the speed of the sun gear, which is a motor, and ring gear, which is the engine. The engine and the motor, so those two speeds are summarized and transmitted through carrier to the output. However, this is not it yet. If you look a little towards the right of the diagram, you can see another set of clutch, which is 48 and 46. This 48 and 46 can be considered as also a dual position clutch. Well, when you engage 48, the rotor of motor 1 is connected to the ring gear of the second planetary gear system. However, if 46 is engaged, then motor 1 motor 1 is just going to be connected to the sun gear of planetary gears 40, which is planetary gear 1. And then 42 or 58, if you look at 58, the ring gear of the second planetary gear will be grounded by 46. So 46 means it's going to lock the ring gear of planetary gear number 2. Okay? So if you look the second planetary gear, which is part 42, in addition to the ring gear, 58 connected to either ground 46 or clutch 48, the carrier is connected to the same output shaft. So the carrier is connected to the same output shaft. And the sun gear in the center, 60. 60 is sun gear. That is connected to motor 2. So think about this. What happens when motor 2 is running, but the ring gear is grounded? Which means motor 2 is going to drive the sun gear of the second planetary gear system, and that torque is transmitted to the carrier, and the carrier is running through the same output shaft. So that mechanism is a torque coupling. Motor 2 and output of planetary gear 1 is a torque coupling. So in this system, you see both torque coupling and speed coupling. Now, the operation also depends on how you put clutch 46 and 48. So that one we just described is ground 42, which 46 is engaged. That is a torque coupling. But if we engage ring gear 58 to sun gear 52, which is sun gear of number 1 and ring gear of number 2 through clutch 48. So what happens, this system becomes a speed coupling. Because ring gear number 2, ring gear of planetary gear number 2, and the sun gear of planetary gear number 2, they are going to be speed coupling. So motor 2 speed is added to the carrier. of planetary gear 2, and that is transmitted to the output. Okay, so let's summarize. In this system, you can achieve both speed coupling and torque coupling based on which clutch is engaged, whether 46 or 48. When 46 is engaged, it is a speed coupling at the planetary gear number 2. If 48 is engaged, this system becomes a speed coupling device. So therefore, that 2 clutches can provide you a lot of flexibility for your system. You can engage 48, so the system becomes a speed coupling for high-speed operation. You can engage 46 for low-speed operation, which is a torque coupling. So that is why GM named this a 2-mode hybrid. And it means that this system can operate at either high vehicle speed or low vehicle speed. 2 different speed operations, 2 mode. That is called a 2-mode hybrid. In 1-mode hybrid, it is either torque coupling, like the Civic, or a speed coupling, like the Prius is partially a speed coupling. But you probably can argue that the Prius also has a 50 kilowatts motor, and then that one is a torque coupling device. Okay, so this is a 2-mode hybrid, and later on I will have some detailed material to disassemble the graph and then show the 2 different operating modes. But at the moment, that I think it's easy to understand that just based on the 2 clutch positions, you can realize either high-speed operation or low-speed operation, which is either torque coupling or speed coupling for the 2 operation modes by using the clutch with 2 electrical motors. So after that GM 2-mode hybrid, apparently there have been some different arrangements to try to manipulate different operating conditions in the system. So therefore, it has come out to be different 2-mode hybrid. The next one we're looking at is a GM 2-mode hybrid variation, where 3 different planetary gear systems are included. So if you look at the very left of the diagram, that's the engine input, and the engine input is connected also to the ring gear, and the carrier is all the way connected to the output. The sun gear is connected to motor A, to MGA. So this part is the same as the previous diagram. However, you can see that the sun gear of motor 1 is also connected to R2, which R2 is connected to C1 or C4, depends on which clutch. So if R2 is connected to C3, then R2 will be grounded, no move. But if R2 is connected to C4, and then R2 will be connected to the sun gear of the 3rd planetary gear systems, and which is also connected to MGB. So now you can see that. The carrier of the 2nd planetary gear is also connected to the common output shaft, which all the way goes to the output. Okay. If you look at the 2nd motor, which is connected to the sun gear of the 2nd S2, which connects to S2, but again, as I said, it can also engage to R2. Okay. And if you look at S3, that is connected to motor 2, and then there's a C2 that can lock the planetary gear 3 carrier. It also can lock R3 through C1. So you can see that C1 and C2 will either lock R3 or PC3. So that depends on which one that you want to control. You can lock either one. Now, when you lock one of them, it's going to change the configuration from the 2nd motor, because 2nd motor is connected to the sun gear. Okay, but depends on which one C1 and C2 is locked. You are connecting. You can basically going to change the speed ratio, how S3 is transferred to the output. For example, if you lock C2, torque of S3 is transmitted to PC3 and to the output shaft. So C1 is locked to ground. So what you can think is that the 3rd planetary gear is a speed reduction gear. in this configuration, just so that you can use a much higher speed electrical motor for your system. Okay. The next one we'll be talking about is a design that was developed at University of California, Davis by Professor Tsai. Professor Tsai looked at the different designs available for hybrids, and he developed this multi-mode hybrid. It's not only two-mode now, it's a multi-mode. Other thing about this hybrid that it only uses one electrical machine instead of two to realize a multi-mode operation. In this configuration, if you look at the diagram, it also involves two plenary gears and two clutches and two locks. The locks can also be considered as a clutch. So if you look at the right hand of the diagram, there's an engine that is connected to C1 and C2. So either C1 or C2 will be engaged at any given time. So if C1 is engaged, the power of C1 or the power of the engine is transmitted from C1 to 2. You can see the path. And 2 is connected to 7, which is a carrier. And then the power of the engine can be split between the ring gear and the sun gear. So if you look carefully, the sun gear, which is number 1, is all the way through to the motor. The ring gear, though, is connected to the carrier of the second one, but then it's also connected directly to the output. So basically, if you engage C1, you're running as a CVT mode, because the electrical motor runs the sun gear, the ring gear runs the output. That's very similar to the previous configuration when you don't have the second motor here yet. So the motor in this case can be either motor or generator, depends on the vehicle speed and the engine speed control. So that's one operating mode. A second mode would be if C2 is engaged. Now the engine torque is transmitted from C2 to number 4. Number 4 is the ring gear. You can see that the ring gear is connected to engine now, and the carrier, which is number 6, is connected to the output. But the sun gear is connected to the electrical motor. So right now, you are also running in the CVT mode, but you are summarizing the speed of the motor and the engine to get the output. So apparently, this when C2 engage, this is more suitable for aiding power of the two input devices. Okay, that's a second mode. You basically can also engage C1. You can engage C1, and now I will tell you you can do many other modes. Now let's look at it. If C1 is engaged, now C1 is driving number 2, and what we're going to do is number 2 is going to drive both. You can see the ring gear and the sun gear. So sun gear is going to the motor, and the ring gear is going to the final drive. Because we have B2 here, we can lock B2. If we lock B2, the motor will not move, which means sun gear number 1 is not going to move. So if sun gear number 1 is not going to move, engine will be able to drive carrier number 2, torque is transmitted to ring gear number 6, and it goes all the way through to the final drive. So in that case, you're running in the engine alone mode, and the speed is in a kind of transmission mode, right? Because the speed is reduced from engine to the output through the set of gears. If you combine different locks and clutches, clutch C1 and C2, lock B1 and B2, you can actually intend 14 different operating modes to satisfy a wide range of speed operations for the engine, for the vehicle. And you can relatively control the engine at a relatively narrow speed range. So this system can give you a lot of benefits by controlling the different operating modes, by controlling the two clutches and the two locks. And with one electrical machine, you can realize all different kind of function, because at one condition, you can run as a motor. When the battery charges to some degree, you can switch to another mode, and then you can use the motor as a generator. When the battery, you charge the battery. So when battery SOC drops low, you change the motor into a generator mode. So it depends on how you operate. And there's a paper on transactions of the SME mechanical design by Professor Tsai. You can read that paper. The next design we're going to discuss is another multimodal hybrid. Well, this model is developed by our group at the University of Michigan. And we are using also one electrical machine and one engine to realize different operating modes that is similar to automatic manual transmission. Automatic manual transmission, which is similar to a manual transmission, but it's controlled automatically. But in the meantime, we can realize also a CVT operation in the system. So if you look carefully that on this diagram, we have an engine on the left, and that is driving a solid shaft. And that solid shaft is connected to a number of gears, 1, 2, 3, and 4. So there are 4 gears which is running on a hollow shaft. So what it means is that those 4 gears are not attached to the engine shaft unless synchronizer is doing something. So you can see that between 1 and 2 there's a synchronizer, between 3 and 4 is a synchronizer. If a synchronizer is in the neutral, the engine does not drive 1, 2, 3, or 4, or any gear. But if a synchronizer is synchronized to gear number 1, the engine is going to drive gear number 1. And that gear number 1 is connected to the output shaft. So engine is driving the output, it's driving the vehicle. So in that case, we have the engine on high speed, high gear ratio, where it's suitable for low speed operation. Now, at the meantime, if you look to the right, there's an electrical machine. And the electrical machine is connected to also a gear. And there's a synchronizer at that place as well. So if the synchronizer is synchronizing the motor, so the motor will be also driving the output shaft. And that's on the right. So at that time, you are combining the torque of the engine and the motor to drive the vehicle at very low speed operations. So that's a typical torque coupling, and it's suitable for low speed operations. At the meantime, you can synchronize gear number 2, or gear number 3, or gear number 4. So by automatically controlling the synchronizer position, you can match vehicle speed. You can match vehicle speed with the vehicle speed in this 4 different speed range. So that's like an automatic manual transmission. That's one operating mode. Even though you can have different gear ratios, but that's one different mode, one operating mode. A second mode is that synchronizer 1, 2, 3, and 4 are all neutral. So at this time, you can see 1, 2, 3, and 4 are neutral. They are not spinning with the shaft. But the engine shaft is all the way driving the carrier of the planetary gear. So the planetary gear, the carrier of planetary gear is driven by the engine. And then the ring gear, you can see the ring gear of the planetary gear is connected through gear number 4 to the final drive. So the ring gear is actually going to drive the final drive. But in the meantime, you see that the sun gear is connected through the synchronizer to the electrical motor. So the electrical motor now can become a motor or a generator depending on vehicle speed and engine speed. So this one is a very typical electrical CVT. So the carrier is driven by the engine, sun gear is driven by the motor, ring gear is driving the final drive. So that's very typical CVT mode. Now, apparently, you can also do engine alone or motor alone, or you can do combined. You can do CVT, and you can do regenerative braking. So all the different modes can be realized in such a system. So again, this system uses one electrical machine, but you can realize different operating modes. In addition to the CVT mode, you can have 4 fixed gear ratios, which you can set the motor idle if you don't, on highway driving, you can set to one of the gears, and you can set the motor idle. So you're directly using a manual transmission, like a manual transmission, to drive the vehicle. You can achieve a much better fuel efficiency, because in a planetary gear-based hybrid, there's always an electrical generator running, and then you're always running a planetary gear system, and your efficiency can get fairly low. And I can tell you, many of the planetary gear systems, when they are spinning, not driving anything, when they are spinning, you can easily get 2 to 3 kilowatts losses in the system. So you can see that by using the system where we are discussing here, you can basically increase the system efficiency for highway driving. But in local low-speed driving, you can take advantage of the CVT. So that's what this system is all about. And then let's move on to the next one, is a Timken two-motor hybrid. The Timken two-motor hybrid is also two-motor hybrid because, again, they also have the high-speed and the low-speed operating modes to realize. So if we look on this diagram, there are two electrical machines, there's an engine. Okay? And then if you look at on the left hand of the diagram, the one marked as output is the one connected to the final drive. The one marked as an input is the one that is connected to the engine. So they marked the input and output both on the same side of the drawing, that's okay. But basically what it is that you put the engine and the driving shaft somewhere in the layout. So the engine is connected to the input, and then that is connected to R1. That is connected to R1, the planetary gear number 1, ring gear. So R1 is connected to engine. And the output shaft, you can see, is connected to the carrier, C1, okay, CR1, or CR1. So that's the carrier. The sun gear of S1 is connected to ring gear of second primary gear system. And the ring gear of the second primary gear system is also connected to E1, electrical motor 1. So now you can see electrical motor 1 to R2, then to S1. So ring gear R1 connect to engine, so motor 1 speed can be added to engine 1 speed and added to CR1 output. So now the output can add the speeds of E1 and engine speed. If you look further at the second planetary gear, where S2 is connected to E2. So E2 is driving S2. So S2, so now because R2 is connected to E1, so if motor 1 and motor 2 both are running, their speed also summarized, and added to the carrier, and you can see the carrier is also connected to the output, connect to CR1, but then also connect to the output. So that's how it operates on these two electrical motors and two planetary gear systems. So if you look inside the two planetary gears, there are two clutches. One is a C1, and then another one is C2. So they can actually, if you look at the C2, there's a B2 as well, which means they can actually ground R2 to B2, so R2 will not move. Or they can actually engage R2 and electrical motor 1. So in that case, R2 will be moving. So therefore, that depends on C2 and R2, the electrical motor 2 can be either stationary or it can be driving R2. Okay? If you look C1, that C1 can actually engage CR1. Okay, it can also disengage CR1. If it's disengaging CR1, and then the whole system will be driven by CR2. But if it's engaged CR1, so both CR1 and CR2 will provide torque or power to drive the vehicle. So it depends on which clutch and where the clutch position is, and you can realize also a high speed and low speed operations. Apparently, in order to understand what exactly the torque and speed relationships, we need to lay out a separate diagram and showing the clutch positions and so on. So we would not have enough time to do the details here. But the idea is that all of this system that described can realize a two-mode operation. And so is the next one, is a Renault HEV Powertrain, where you also have two planetary gears, two electrical motors with two different operation modes, high speed and low speed. Now this moment that the engine now is shift and then both the final drive on the right hand, but that's okay. It's just the way how you draw the diagram. So you can see the engine is connected to C2. The engine is connected to C2, and C2 is connected to R1. Okay? There's no clutch in this diagram. The output is connected to R2 and also connected to C1. So that's output. Engine MG1 is connected to S1. MG2 is connected to S2. So both S1 and S2 are driven by electrical motor. C1 and C2, C1 is connected to the final drive, but C2 is connected to R1. So torque from C2 can be transmitted to C1 and then transmitted to the final drive. So again, the relationship between the two motors and the engine would have a set of relationships. Because there's no clutch in this system, you can only realize one set of operating mode. This is not a two-mode operation. This will be one mode. So in fact, one of the planetary gear system will act like a speed reduction, but the other one is actually acting as a speed coupling device if you derive the detailed relationship. And the relationship can be easily derived because if you look at the system like this, there is a fixed, we can probably simply go through this derivation, just give you sort of idea how to analyze a different system like this. Now let's look at the planetary gears relationships. We will go from left to right. Left one is planetary gear 2. So you can see that C2 speed, let's see, the C2 speed, so omega C2 is equal to engine speed. And R2 speed is equal to vehicle speed. And S2 speed is equal to omega motor 2 speed. And Zhang gear 1 speed is equal to motor 1 speed. So these are the two speed relationships. And then in the two planetary gears, we can write that omega C2 would equal to omega R2 times, let's say, NR2 plus, NR2 plus NS2. And then this will be NS2 divided by NS2 plus NR2 times omega R2, which we know that R2 is equal to vehicle speed. Okay, so that's one expression. So omega R2 is equal to omega vehicle speed, which is shown here. The second relationship would be omega C1 is equal to NR1 divided by NR1 plus NS1 times omega R1 plus NS1 divided by NS1 plus NR1 times omega. I'm sorry, this is RS2. We're going to make a correction here. So omega R2, and this is omega S2. So this is omega S1. So that's your second relationship. And we know that omega C1, if you look carefully, omega C1 is connected to R2. So omega C1 is equal to omega R2. So based on all these set of equations, you can easily derive vehicle speed is equal to omega R2. And omega R2, if we mark this as equation number 1, can be derived from equation number 1 as a function of omega C2 and omega S2. And omega C2 and omega S2, and we mount is here, this set of relationships, okay? And then we can plug in the second equation to all this equation. Then you can get omega vehicle speed as a function of omega M1, omega M2, and omega engine. So it can be easily derived for all these three systems. Now, in particular, This system doesn't have a clutch, so it's easy. Now, if you have a clutch, what are you going to do? Well, you really have to determine, what you need to do is to analyze each one for each clutch position. So you would fix clutch at one position, analyze the system to get one set of equations. And then you put clutch at another position to derive another set of equations. In the GM two-mode hybrid, you have basically, even though that's two clutch, but even that's only the two positions for R2. Now for that Timken hybrid, you may run into 4 different operations because there's two separate clutches. You can have clutch 1 engage, 2 open, 1 open, 2 engage, and both engage and both open. So 2 different scenarios, but the 4 different scenarios only have 2 are valid. The other 2 are not going to work for your system. So you're going to analyze the 2 different scenarios for the systems. So up to this point, we basically covered all different topologies available for hybrid and plug-in hybrid configurations, which means you can use any one of these hybrid systems to build a hybrid or to build a plug-in hybrid. You can build your powertrain. Now, of course, some of the patents are owned by some suppliers or some OEMs, original equipment manufacturer. We refer to the auto car makers. The suppliers, they supply components to the OEMs. So those two, and all these designs couldn't be owned by some companies. So therefore, it may not be free to use. But some of the diagrams may be available already, or the patent may have already expired. So you can basically find the system. But all these topologies, again, they are only showing the operating principle. In order to realize detailed control, to control the clutch, to control the synchronizer, there is a lot of additional effort in real life. And then you have to design the control system that would operate such a powertrain. So in any case, no matter which powertrain you're going to use for your hybrid, for your PHEV, you're going to need motors and power electronics for your system. You may need 2 or 3 or 1 electrical motor and associated power electronics for your hybrid, plug-in hybrid vehicle system. So this portion is new. Traditionally, our vehicles, conventional vehicles, whether powered by gasoline engine or diesel engines, they don't have powertrain motors. You may deal with smaller DC electrical motors that